Hello, Matt G4IYT here. Today we're looking at the full license mock examination number 1, version 1.6, and we've reached question 32, which reads, how long is a typical half-wave dipole tuned for the center of the 1.8 MHz band? So we will of course recall that a dipole is two elements like this, so it's a balanced antenna fed in the middle there, and then the total length of these elements is going to be the wavelength over 2, lambda over 2, which is why we call it a half-wave dipole. And we're being asked about one that is tuned for the center of the 1.8 MHz band, so it would be a good starting point to figure out where the center of the 1.8 MHz band is. And we're going to flip over to the EX309, the reference data that you'll get for use in the full level examination, and we're going to look for license parameters. There we go, full license parameters, and it gives us a list here of a load of bands that you may be asked about in the exam, and things like the frequencies and the status of the amateur allocation in that band. And it is important to cross-check with this sheet. There are occasionally changes to where we can operate, and the exam questions will be based on what's in the EX309, not necessarily what you may use on the band. So definitely worth double-checking. It costs you nothing to do that in the exam. You have the sheet right in front of you, so always worth double-checking. And we can see here that we've got the 1.8 meg band starting at 1.81 megs, and it goes all the way up to 2 megs. So to find the center, we can just take the average of this lower band edge and the upper band edge, and that will give us the midpoint. So we can do 1.81 megahertz plus 2 megahertz and divide that by 2, and that gives us 1.905. So the center of the 1.8 meg band is 1.905 megahertz. Not going to get all that in, am I? So the next thing we want to figure out is our wavelength lambda, and we may recall that the wavelength lambda is equal to the velocity of the radio wave divided by the frequency. And the number we commonly use for V here is the velocity of a radio wave in free space, which is 300 million meters per second, give or take. However, I like to simplify this, and you can actually do it as 300 divided by the frequency, but keep the frequency in megahertz. So if you did it with the long number, the full 300 million meters per second, you'd have to put in the frequency in hertz. If you keep the frequency in megahertz, you can just use 300 as the top number, and the ratio works out the same. So let's do that now with our frequency that we've got. So we do 300 divided by 1.905 megahertz, and that gives us this wavelength here of 157.48 meters. And we can see that as an answer here. However, that is incorrect, because that is the full wavelength here, and we're looking for the half wavelength. So we need to divide that by 2, and that gives us the answer of 78.74 meters. And it would be really tempting to select this as the answer here, and that's exactly what I did the first time I saw this question, but that is in fact wrong. And the reason that it's wrong is because of this V, this velocity factor that this velocity that we've chosen for calculating our wavelength. Now, that is the velocity of a radio wave in free space. However, our antenna is not made up of free space, it's made up of some kind of metal wire, and the speed of a radio wave through that material is going to be slower than it is through free space, and we express that as the velocity factor. So a material might have a velocity factor of 0.9, which means that radio waves travel through it at 90% of the speed that they would travel through free space. Now, a good starting point for a velocity factor for example, a wire that you'd use to make an antenna is about 0.95, and because our radio wave is going to travel more slowly through our half-wave dipole, we then only need to have a shorter half-wave dipole. So we can multiply this half-wave length by 0.95 to make it 95% of the length, because the radio wave is going at 95% of the speed. So let's do that. Multiply by 0.95, and that actually gives us an answer that is much close to 75 meters. So again, it's because the speed of the radio wave through our antenna is going to be slower than the speed of the radio wave through free space, and we figured out our wavelength based on its speed through free space. So we need to include the velocity factor as part of that calculation to get to the right answer. So let's skip down to the answers and see if we got that one right. And yes, of course, we can see for question 32 the answer is in fact B. So yeah, make sure you include that velocity factor when doing calculations on your antennas. Thank you very much. I'll catch you for the next one.